Welcome to the Plotacy channel. I'm Robert, and today we're doing a quick intro to the Wombat2 programming language design because I want to talk about the type system, which I think might have wider applicability, but I need some context to talk about it. And rather than mixing all this stuff in with the type talk, I've separated it out. Wombat2 is inspired a bit by the fact that I think mathematics and programming are similar. They're about thinking clearly about problems, and the nice idea is that proofs are programs and propositions are types is the route to combining them in a way that's of benefit to both. We separate out effects which have time-dependent semantics from procedure calls which conceptually all happen at once. They happen outside of time. And I guess all I really want to say here is that we won't be talking about effects because they're not too relevant to the type system. So the first thing we need to know about is atoms. Atoms are formed by a dot followed by an identifier like .xyz, .size, something like that. And the things that you'll see in Wombat2 that look like a method or a field access, they're always just a procedure call. So f.xyz is the same as f space.xyz or f.xyz in brackets. It's a application of the procedure f to the value.xyz. And this works to a significant extent because values of various types convert naturally into procedures. So, for example, if you've got a string and you put the dot length method access after it, that's really what happens is that the string gets converted into a procedure that takes dot length and returns an int. Now, and that procedure is just an ordinary procedure, and the conversion is just an ordinary procedure, except that it's implicit. So identifiers come in two categories. They either stand for a constant thing or they're free, which we'll come to. A constant thing could be a memory address where the contents of the memory location change, but we don't think of that as a change in the identifier. At any rate, a new identifier is indicated by prefixing it with a back quote. That's just so that we have lexical scoping, so that's to say that it's not the same as the same identifier at a higher level, and maybe also the same identifier as it's a different identifier from ones in other imported code. Now, free identifiers, by contrast, are just placeholders which some people like to replace with point-free style, but point-free style is something most of us have a lot of trouble with. So free identifiers are placeholders in some sort of universal for all type situation. So example here of the definition of the factorial, we could say for all n, which is a natural number, the factorial of n plus 1 is n plus 1 times the factorial of n. So you can use for all, but that gets annoying, and so we have another rule, which is that you can introduce a free variable with double backticks, and that will create an implicit for all. So the example here we have is exactly the same as the previous one. It's just that the for all is constructed to contain all instances, to the smallest expression that contains all instances of the identifier n in this case. So types can be simple, like int and string. More commonly they come in indexed families, like a list of x. A tuple takes a list of types as its parameter, and the indexes aren't necessarily other types. They could be, so vect takes a length as well as a type, and these index types are more or less the same as dependent types, I think. Now, types of value type. This normally doesn't cause any trouble, though. If it's threatening to, we can say they actually belong in a higher universe, and I should sort all that out. Okay, just to make a bit of an explanation of how dependent types work. At execution time, we have access to a values type, but typically a lot of it's known at compile time and doesn't need to be kept at runtime. But that's not necessarily the case. So the n in vect of n comma x might have come from an effect. It might have been read in some way from a database or something. So the value is the actual data plus the relevant data from the dependent type, and that data might in turn have dependencies, and so theoretically we get a stack of these things, though in practice it really rarely goes very far. And why not just store all that stuff in the value and only have simple types? It turns out that dependent types are the natural way of breaking things down so that we can think at the right level of abstraction. And they fit at exactly the right, they're the sweet spot between dynamic typing and static and completely static typing. Procedures which have type proc x comma y have one input and one output. Of course, they can be compound things. Procedures can be explicit closures, which we'll come to, or they can be primitive things, or things that are created by some primitive thing. Now, a closure is just a thing in braces. It's just an expression in braces, and it has type proc any comma any. Now, the argument for this is that since procedures can fail, expanding the input to any just increases the number of things on which it can fail. That doesn't actually change much. And of course, procedures rarely output the whole of the output type. So just expanding the output type to any doesn't change a lot. The real point is that we can coerce the thing to what we want, as I show in the following example. The input to the procedure is the no-fix operator $. Yes, I know people don't like this, but anyway, it makes life easy, and basically we can easily unpack $, as the very first thing we do, and that's not a lot. It doesn't turn out to be a lot different from specifying it, associating identifiers with the input in some other way. So here's an example of the factorial thing. It's basically the same code as we saw before, except we give it as a closure, but we immediately coerce it to be a total procedure from nat to nat, and in fact it's actually an embedding as well, which is another story that we'll come to. Right, so tproc, total procedures, these never fail, and these are very important as types for many applications. So they have their own little operator, which is a right arrow with a double, starting with a double equals, and these also have their own special closure type, where instead of opening with a brace, we open the brace in a quote, a single quote, or a prime, as they're sometimes called, and and we specify the input and the output, and then we have an expression which is just the same. Invertible procedures are very important as well, and they have their own subtype, which is t embed x comma y, and their own way of being written. Now, an embedding means that embedding, like t-procs, they always succeed going forward, but backwards, of course, commonly doesn't succeed because there are values of the output type of y that didn't come from any x, so they can't be inverted. Now, as I say, we're doing dependent types here, and this all comes in a collection of other dependent things, and dependent procedures are one of them, where the output type of the procedure is allowed to vary depending on the input type. And syntactically, we have a convenient way to write that, which was that we just put the output type in braces and provide the expression for the type in those braces. And similarly, for closures, we put the output type in braces, and we don't need to specify the input and the output, because the input is obviously the input type of the procedure, X in this case, and the output has to be type. So this is implicitly coerced to X goes to type. So if we, going back to our simple dependent type example, vector is from nat times type goes to type, which means that if we have a vec type, we can go backwards to find out what the n and the type were, by the way. That's why it's an embedding. All right, suppose, so there's a natural thing with this where if we can do an append. So if we have a tuple and we have a vector of n and x and another vector of m and x, where we're introducing n and x and m as free variables. So this is all in one giant for all. The output is a vector n plus m of x, naturally. But if we want to convert a list to a vector, then the output type depends on the length of the list, which is not known at compile time. So this is an example of a dependent procedure where the n part of our vector n comma x is $.length, which is the length of our list. All right, structures fill the role of dependent pairs, which appear in some languages. So this has the form of a bracket, left square bracket, and a prime, followed by an expression and a right square bracket. And the result of the expression is ignored, and the identifiers introduced, which can reference each other, are given types in the body of the expression. So a value of that structure type sets those identifiers to values of the right type. So I'm giving a simple example here where there's no actual cross-reference between the identifiers, but that's not my useful application of it. So our string int structure has a string and an integer. We can create a subtype by, of course, I'll have more to say about subtypes in the next video. We can take a subtype by setting a value for the integer. We can create another subtype by setting both of the string and the integer, but it's still actually a type, even though it only has one value. That's why we have to put in the third line an at in front of the thing to get the value of the type. And we can just print it out in that way. So we see si.s inside the structure S is an identifier and can be accessed inside that structure just as if it was an identifier. But once you're looking at the structure from outside, you use the matching atom to get at the value inside. And as we'll eventually see in later videos, these sorts of structures work well for mathematical structures like groups, where we have the operations and the laws relating to those operations all in one nice, neat place, referencing each other. All right, so the next video will be on the type system itself, and I'll see you then.